Let's have a look at worksheet number 8 on electric fields. Yesterday we learned that an electric field is a region of space in which an electric force could be experienced by a charged particle. A region of space in which an electric force could be experienced by a charged particle if there was a charged particle there. That takes us to the definition of the direction of the electric field as well. We define the direction of the electric field as the direction of the force on a, what type of particle? The direction of the force, or the direction that a blank particle moves when placed in the field. On a positive particle, right? The direction of the force on a positive particle, the direction the positive particle moves when placed in the field. We could have defined it as the way the negative particle moves when placed in the field, but we didn't. Okay, it's arbitrary, but it is what it is. The direction that a positive moves when placed in the field. So if you have a field to the right, then the positive particle would experience a force to the right. If you have a field to the right, a negative particle would experience a force to the left. Okay? Positive particle experiences a force with the field. A negative particle experiences a force against the field. Remember the quote we did yesterday? I'm positive the force is with the field. That's just a little reminder that if it's an electric field that points one way, then the force on a positive is the same way. And we just have to remember that a negative is opposite to that, right? Okay, let's take a look at number 3 and number 6 on that worksheet. They both use the two equations. One of them uses the first equation that we learned yesterday. One of them uses the second equation that we learned yesterday. We'll see which is which here in a second. 3 says calculate the strength and the direction of the electric field, 8.5 centimeters. I want to circle that because I don't want to forget to convert that to meters. To the left of a positive 300 microcoulomb electric charge. The strength and the direction of the electric field. Let's draw this out, okay? Drawing it out is going to help us with the direction, but it's also going to help us to determine whether we have a producer or an experiencer here. 8.5 centimeters to the left of this charge. So here's my charge. Okay, I want to find the field strength right here, 8.5 centimeters to the left of that charge. Is that point X, okay, is that point X where the charge is? No, the charge is over here, right? Where we're trying to find the field is over here. All right, so we know something about this charge right here. Is this charge producing or experiencing the field at point X, where I'm trying to find the strength of the field? Is it causing it or is it feeling it? You can't feel something if you're not there. Okay, it's supposed to be 15 degrees outside today. I can't feel the 15 degrees outside if I'm not outside. This charge can't experience or feel the field at this point because it isn't there. So it must be therefore a producer, right? So we're going to use the producer equation, which is E is equal to KQ over R squared. K is, of course, 8.99 times 10 to the 9. Q is 300 times 10 to the minus 6 coulombs. Okay, forget that conversion factor, just check your data sheet. Just replace the micro with 10 to the 6. Now, that's a positive charge, so of course we're going to sub it in as a positive charge. But even if it was negative, we'd still sub it in as a positive charge. Right? We drop the sign of the charge always when we sub it into an equation. R, 0.0850, and we square that. When we do that math, we end up getting a value here of 3.73 times 10 to the 8 newtons per coulomb. Now, what about the direction? The answer I told you when I gave you the answers to this worksheet, I told you the answer was to the left. Okay, how do you know it's to the left, though? How did I know it was to the left when I told you that it was that way? The electric field is the way that a positive particle moves when placed in the field. It's also defined as, yes, away from the positive. Away from the positive. Okay, we're to the left of this positive producer here. It's going to be away from that positive producer. Why is it away from the positive? Well, because if I put a little positive particle in there, it would experience a force to the left. It would be repelled and therefore be pushed to the left. So it's the way that a positive moves, but it's also defined as away from a positive producer and toward a negative producer. Got it? Okay, the other question that we're going to go over is question number 6. It says find the magnitude of the electric field experienced by an alpha particle if the net force is this we're going to find the acceleration of the alpha particle as well. If the alpha particle experiences a force, then it must be an, there's your hint right there. It's not it's an experiencer. It's experiencing the field. So we're going to use the experiencer equation. We're going to say E is equal to F over Q. The force is 2.00 times 10 to the negative 16 newtons, divided by the charge here of the alpha particle, which on our data sheet is 3.20 times 10 to the minus 19 coulombs. We do the math on that one, and it works out to be 6.25 times 10 to the 2, or we could just say 625 newtons per coulomb. Now, we want to find the acceleration. Okay, what's the rule in physics 30 when you're looking for acceleration? The force needs to be with you, right? The force needs to be with you. May the force be with you. Hey, guess what? It already is. Okay, this one, it's given to us in the question. 2.00 times 10 to the negative 16. So we don't have to find anything first. We just take that force that we're given, divide it by the mass here. Okay, 2.00, the mass is 6.65 times 10 to the minus 27. We get an acceleration here of 3.01 times 10 to the 10 meters per second squared. Now, that is the initial acceleration because this charge, this alpha particle that's experiencing the field and the force is going to move as a result of that, right? So distances are going to change, and therefore the field's going to change, and therefore the force is going to change. And if the force changes, then the acceleration is going to change. But initially, this is what it is. Does that make sense? All right, I want to do one more example with you here right now. Example number 3 says determine the magnitude and the direction of the electric field midway between these two charges. I'm going to circle this to remember to convert. Circle this as well to remind me that it's a negative charge. And circle this. All kinds of things to draw attention to in this one. Draw a picture of this, right? We got a 100 microcoulomb charge right here. 100 times 10 to the minus 6. We have another one over here that's, it's negative, and it's negative 75 microcoulombs. And then we have a distance here that's 20.0 centimeters. We want to find the field strength right here, midway between, halfway between those two charges. Well, we got to draw almost what we drew in our last topic with the electric forces. We have to draw what almost amounts to a free body diagram. It's not technically a free body diagram because free body diagrams show only the forces that are acting on something. This is going to show electric fields. Let's show the electric field here caused by the first one. Let's call this one A. And let's call this one B. The electric field caused by A at that point is to the right. Anybody know why it's to the right? Forget about B. B doesn't exist to us right now. Yeah, because it's a positive particle, right? And the field points away from a positive particle, right? So it's going to point to the right. What about B? What about the field caused by B? Which way is it going to point? Yeah, it's also to the right. And why is it showing going to point to the right? Yeah, well, the negative is the producer here. B is the producer now. We're pretending A doesn't exist. Okay, and the field points toward a negative producer. So the blue field is away from the positive producer. The green field is toward the negative producer. And they both end up being to the right, as it turns out. Now, let's calculate the field caused by A. The field caused by A is KQA over R squared, right? Because A is a producer. We're trying to find the field strength not where the charge is, so it must be a producer. KQA over R squared. That's 8.99 times 10 to the 9 times QA, which is 100 times 10 to the minus 6. Don't forget that. We're less likely to because we drew attention to it with the red circle. Over R squared. What's the value of R? 0.20, right? Yes, correct. It's 0.10. Why is it half, Sean? Yeah, we're trying to find the field strength in the middle. And the distance from charge A to the middle is half of that distance, 0.1. So we do the math on that one. We end up getting 8.99 times 10 to the 7 newtons per coulomb. There's the first one. And then the second one, EB, is KQB over R squared. It's 8.99 times 10 to the 9 times QB, which is 75 microcoulombs, or 75 times 10 to the minus 6, over same distance again because it's midway between. The field we get there is 6.7425 times 10 to the 7. Now, how do you think we're going to combine these two fields? It's easy now, right? How do we combine those two fields? Both to the right, we're just going to add them up, right? EA plus EB. Don't forget those little vector signs because you'll mix it up with energy at some point. EA is 8.99 times 10 to the 7 plus 6.7425 times 10 to the 7. We add those up, we get a value of 1.57 times 10 to the 8 newtons per coulomb. And we got a positive value, so it means it's to the right. How would that have changed if EB had been to the left? Yeah, we would have added, but we would have added a negative number, which is the same thing as subtracting, right? It's almost like those 3-charge force problems, right? You got 3 charges in a row, what's the force on the middle charge? Except that we're not finding forces, we're finding fields. So for that, you only need 2 charges. Your 2 questions for homework tonight are worksheet number 8, questions 8 and 9.